Hi everybody. Today we're going to start our unit on circles, unit 4.2. In today's lesson we're going to learn about some specific properties of tangents and other special segments in circles. A circle is defined as the set of all given points in a plane at a given distance from a given point in the plane. So that given point is called the center of the circle. So if we draw a circle, that given distance is called the radius. So imagine if we went the same distance in every direction from point A, that's how we would create a circle. So the center is point A, the radius is the distance from the center to a point on the circle. All right, a chord is defined as a segment whose endpoints lie on the circle. So for example, if we had that circle A, and I drew a line segment so that its two endpoints B and C were right on the circle, we would say that this is chord BC. So check out the notation, just looks like the notation for a segment. A diameter is defined as a chord that contains the center of a circle. Another way of thinking about this is that a diameter is the longest possible chord. So if there's the center and we have chord AB and it goes to the center, it's a diameter. A secant is a line or a line segment that contains a chord and it's going to extend. We say it extends beyond the circle. So if we had this circle and we did this, let's call that CD in this picture. CD would be a secant. So it contains a chord. The chord would be this line segment right here from C to D. But because it goes through the circle and continues on, we can call it a secant. A tangent is a line in the plane of the circle that intersects the circle in exactly one point. So if we draw a circle, and I draw a line so that it touches the circle in exactly one point. Let me try that again. So let's start with a circle. Clean that up. And if we have a line that just touches in exactly one point, then we would say that this is a tangent. So say line AB is tangent to the circle at point A. Okay, so we're going to add some pictures to a diagram. So let's take a look at that. In example 1, actually we're just going to name the special pieces. In example 1 it says use the diagram to name each of the following. So for part A, it says we have to name a radius. There are actually 3 possible answers here. So we want to start from the center and go to a point on the circle. So AC, line segment AC is a radius, line segment AE is a radius, and line segment AD is also a radius. Okay, for a diameter, recall that that's a chord that has to go through the center of the circle. We only have one possible answer here, and that is line segment DE. Right, CA, again, is only a radius. It stops at the center, so it's not a diameter. FG doesn't go through the center, so it can't be a diameter. Right, a tangent touches the circle in exactly one point. Right, so line CB would be our tangent. And a secant is a line or a segment that goes through the circle and continues on, and it has to contain a chord. So line FG fits that description. It contains chord FG, and it continues on beyond the circle. Now, as far as chords go, we have a couple of possible answers here. Remember that a diameter is also a chord, so you could say line segment DE. That is definitely a chord. Let's clean that up. I don't know what happened there. And you can also say line segment FG. Don't put the arrows on. We just want to talk about this portion of it and nothing else. Okay, our first theorem for today says if a line is tangent to a circle, then the line is perpendicular to the radius drawn to the point of tangency. So if we have a radius drawn out to this point, and we also had a tangent segment, saying this segment only touches the circle at one point. What this is telling us, what the theorem is telling us, is that this radius would be perpendicular to that. So let's call this tangent BC. So AB would be perpendicular to line BC at the point of tangency, at point B. Now if you check this out, here's what we're going to see quite a bit of. You can turn this into a right triangle if you have another segment drawn. Okay, so it's really good for solving problems if we know that the radius is perpendicular to the tangent at the point of tangency. Our second theorem for today simply says tangent segments from a common external point are congruent. So if we had this point out here that I'll call point A, and let's say this is a tangent segment here. Let's try that. It's hard making this without a ruler. If we have tangent segment here, they're tangent here and here. Those are the points of tangency. What this theorem tells us is that these two segments would be congruent to each other. So if this segment is 8 inches long, this segment would also be 8 inches long. So some more practice, some other examples. It says, is DE tangent to circle C? All right, should be, is BD tangent to circle C? Okay, we want to prove that it's tangent by proving whether or not that is a right triangle. So we're going to do 3 squared plus 4 squared. We're using the Pythagorean theorem. And then we're going to set it equal to this whole side squared. Well, we only know that this piece is 2, but from the diagram we know that this radius is 3, so this radius has to be 3, making this whole side 5. So if 3 squared plus 4 squared is equal to 5 squared, then it is tangent because we'll have a right triangle. So we have 9 plus 16 equal to 25. Yeah, 25 is equal to 25. So yes, line segment BD is tangent to circle C. Okay, in example 3, it says that ST is tangent to circle Q. We have to find the value of R. So R is a radius, and again, draw an R here. That makes this whole hypotenuse R plus 18. So if we set it up in the Pythagorean theorem, we want to do R squared plus 24 squared is equal to R plus 18 quantity squared. Okay, so if we do the math there, we have R squared plus 576. That's 24 squared. Now, when you do R plus 18 quantity squared, we need to write it out twice and use the FOIL method to multiply these two binomials. So we have R squared plus 576 is equal to R squared for the first terms, plus an 18R for the outer terms, plus another 18R for the inner terms, plus 18 squared on the end. And 18 times 18 is 324. Okay, well, the good news is that we won't have to solve a quadratic equation, because if I see here, I can subtract r squared on this side. I have to keep it in balance, do the same thing on the right-hand side. So I now have 576 is equal to all of this. And I'm going to simplify that. Combine your like terms. 18r plus 18r is a total of 36r plus that 324. Okay, subtract 324 from both sides. So 576 minus 324 is going to leave us with 252. And that's equal to 36r. Let me scroll down just a little bit more. We need to take and divide both sides by 36. We end up with r is equal to 7. Final answer. So the radius of our circle would be 7 units. Okay, one final quick example. In example 4, it says we have to find the value or values of x. Now, they don't tell us in words that these two segments on the outside that are labeled with 9 and x squared are tangent segments, but we have another hint that we can take away. You see how they're perpendicular to the radius here? This radius is perpendicular to that segment. That means that these two segments are tangent segments. And when tangent segments meet at a point outside the circle, they are congruent to each other. So we can set x squared equal to 9. And then to solve for x, you just need to take the square root of both sides. So you get x is equal to plus or minus 3. So it could be positive 3 for x, or we could use negative 3 for x. Final answer. Okay, good luck on your homework, and please let your teacher know if you have any questions.